So over the last few minutes, much has happened. So let's just do a summary and make some comments, okay? And then we can have some discussions. Okay. Number one is, as I said, e to the power minus alpha of kBt. This factor is known as the Boltzmann factor. And the Boltzmann factor expresses, the probability that your system is in the state with energy E alpha. Now, what the Boltzmann factor is saying is that for states whose energies are greater than kBt, those states, the probabilities are exponentially suppressed. Right? As you know, when we use in nuclear physics half-life is the time after which the radiation is exponentially suppressed. Here it's the same thing. But for energies less than or equal to kBt, the probabilities are all comparable, right? So probabilities are all comparable. So we can find the system in any of those states. So that's comment number one. Comment number two is that the partition function z is a normalization constant. But it's as a function, it's a very important constant. In fact, we'll see that all of the important quantities, almost all of the important quantities of statistical mechanics or canonical ensemble can be derived from Z. In the tutorial, you saw how the average energy and the specific heat, or the heat capacity more specifically, was derived using the partition function, right? Number three is that we often use the standard notation where beta is 1 over kBt. In high energy physics and in cosmology, it is often kb is often set to 1. In those units, beta is 1 over t. That beta, that t itself has the dimension. In those units, t itself has a dimension of energy, right? But in these units, right? And next comment is that if you have two independent functions, two independent systems, then of course their total energy, this will be a sum of their individual energies, right? So therefore,
Sir, what does it mean by two independent systems?
right, you have system 1, you have system 2. They're not talking to each other or not doing anything with each other. They're just like, you're just like, bringing them together in a way that nothing exciting happens between them. They're not
I
interacting.
mean, they can't even exchange energy with each other.
Sorry?
Like, they can't even exchange energy with each other.
No, they're not exchanging energy. So you can define their total energy to be the sum.
No.
This is just a trivial. I'm just saying that when you, so for example, if you have a lattice, for example, right? If you have a lattice and, and suppose you take this part of the lattice and you want to consider this part of the lattice, and they're far away from each other. They're not really talking to each other. They're being screened by all the stuff that's in between. But you, for some whatever reason, you want to consider them together, right? Maybe as a first approximation, and maybe you don't want to consider the interaction between all the systems anyway, right? That we can always do stuff like that in a limit where we are looking at weak interaction, for example. You may want to do this. That's all I'm saying. So in that case, our partition function is going to be e to the power minus beta em, energy of the system 1, and en, the energy of the system 2, right? Which kind of means that, because this is exponential, it factors, and then, so for independent systems, the partition function just factors into two partition functions. Okay, so these are my comments on the partition function, and please let me know if you have any questions. Okay.
So would you please
Oh, yeah.
scroll
So
up?
there's a question. So what does the omega represent in the equation? Which equation? Okay, let me see. What does omega represent in the equation? Omega. Okay, this omega, right? So this omega represents the total number of configurations of the reservoir whose energy is this. Okay. All right. Thank you. Okay. Any more questions?
So would you scroll down a bit?
Yeah. More?
A bit more. Yes. The summation containing equation. A bit up.
Yeah.
The summation of alpha and what is the end limit of this summation? Like we are adding up all, we are including all the possible energy states in this partition
Exactly.
function.
Yeah. Yeah.
Sure.
This summation can, in principle, be an integral. And it could be over an infinite range. It could be over a semi-infinite range. It could be over a finite range. So this is, we are setting aside, issues of convergence and stuff like that here.
Okay. And what did you mean by exponentially suppressed and then another part comparative
Right.
or
So what I mean is that this is the Boltzmann factor. And if the energy is larger than kBt, then the argument of the exponential is smaller than -1. Right? So if I look at this function, what does it look like? It looks like it looks
climbs
something like
down
this. Yeah. Sorry, it should be more.
to the
It
left.
goes, yeah, to the left. No, this is E.
Oh,
E is this way, okay? And over here, this is e to the power minus e by kbt. Okay, so sorry, this doesn't blow up at 0. I should read. So at e equals to 0, this is 1, right? So this is starts like this. Sorry, my drawing is not very good today, and also because the iPad screen is very slippery. Okay, yeah, that's it. So this goes to 0 rapidly. And over here is the point where the value of E is kBt. And here the value of the function compared to the value here is 1 over E, right? So what we're saying is that as the energy is increased, the probability of the system being in this yellow region is very small, right? Whereas the probability of the system being in the pink region is very high. Okay. I mean, this is basically what we do when we are talking about, say, half-life, right? We say that, after our half-life, after 1 EF of the, the radiation is very small, right? Is that clear?
Yes, sir.
Okay. Any more questions?
Sir, the fact that you call the partition function a constant, is that because it always adds up to 1?
The partition function does not add up to 1. It's a normalization. The probabilities add up to 1.
All right. So in what way is it a constant?
It's a normalization constant in this sense, because we are.
I see. Okay.
Yeah. Okay. It doesn't depend on E, right? It's because you're summing over E.
Yeah.
But you can still manipulate it because you have the functional dependence on E, and therefore you can still manipulate it, right?
It depends on beta or T.
Exactly. Yeah. So it depends on beta. It's a function of beta. Exactly. In fact, I think in the tutorial I did show that they did write that it's a function of beta, but for convenience we just don't write it. I think in the tutorial I did say that this is, and then you take derivative with respect to beta, and it's analogous to what is known as a generating function in mathematics, or at least it's very closely connected to that.
You mean like generating polynomials like that?
Yeah.
Those
generating functions are very Legendre polynomials. It's in spirit it's very close to those things. You'll see that. I mean, I think you'll see that in the future. We have to introduce some kind of a source, but you'll see that. It's not obvious right now, but it will. Yeah. Okay, let's. Any more questions?
So would you explain the comment number 2 again?
Okay. Comment number 2 is Z is a normalization constant, and all important quantities of canonical ensemble, such as E and CV, and also the free energy, stuff like that, you can derive from Z of beta. Okay, and that's something. Did you do that tutorial day before yesterday?
I didn't contribute, but I was an spectator.
Okay, so if you go through the tutorial, you will see that having a knowledge of Z allows you to derive these quantities, and we will see this in a moment.
Okay.
Okay.